Part 4, you will hear a university lecture about weather radar and severe storm tracking. First, you have some time to look at questions 31 to 40. Now listen carefully and answer questions 31 to 40.
In this lecture, I will introduce how weather radar helps forecasters monitor severe storms. Radar does not take a photograph of clouds. Instead, it transmits energy and analyzes what comes back from precipitation or other targets in the atmosphere. A modern weather radar sends very short radio wave pulses. These transmissions last only a very small fraction of a second, and they are repeated as the antenna turns. After each transmission, the radar pauses and listens for returned signals. By measuring how long those signals take to return and by recording where the antenna was pointing, the system can estimate the distance and direction of the target. One of the most familiar radar products is reflectivity. Reflectivity describes how strongly targets send energy back to the radar. Large raindrops, wet snow, or hail can all produce strong returns, so reflectivity is not simply a picture of rain. However, algorithms can use reflectivity to estimate rainfall, especially when combined with other information such as the height of the beam and the type of particles detected. This is why radar rainfall estimates are valuable, but they still need interpretation. Doppler radar adds another important measurement. It can measure radial velocity, meaning motion toward or away from the radar. This is useful because storms are not only areas of rain. They are moving systems with internal wind patterns. Tight changes in velocity over a small area can suggest storm rotation. Forecasters examine that rotation carefully because it may be associated with severe thunderstorms. They do not issue warnings from one image alone, but a persistent area of rotation can become an important sign that the storm is organizing. A later upgrade is called dual polarization. Earlier radars mostly used one orientation of signal, while dual polarization uses both horizontal and vertical orientations. This helps forecasters identify the size and shape of targets. That distinction matters because two areas can look similar in reflectivity while containing different types of particles. A cluster of large, irregular targets may indicate hail, while a smoother pattern may indicate heavy rain. Dual polarization is also useful for identifying non-weather targets, such as birds, insects, or smoke. Those returns can appear on radar screens, particularly during migration or near fires, so forecasters need tools that help separate meteorological signals from other objects in the air. This is also why training and local knowledge remain important. Radar still has limitations. At long range, the radar beam is higher above the ground because the Earth curves away beneath it and the beam itself rises with distance. This means low-level features near the surface may be missed far from the radar. Mountains can also block part of the beam, creating areas with poor coverage. In addition, radar cannot tell a forecaster everything about what is happening at the ground, so spotter reports and surface instruments remain useful. For that reason, radar is only one part of severe weather monitoring. Forecasters combine radar with satellite imagery, surface observations, lightning data, and reports from trained spotters. The value of radar lies in its speed and detail, but it must be interpreted in context. So, weather radar is best understood as a measuring system. It provides information about returned energy, motion, target type, and storm structure. Used carefully, it can support earlier warnings and better decisions when hazardous weather is developing. The key point for students is that radar data are measurements, not automatic conclusions. A forecaster must judge whether a pattern is meteorologically meaningful, whether the radar view is limited, and whether other observations support the same interpretation.
That is the end of part 4. You now have some time to check your answers.